As I mentioned, our speaker today is Patrick Organ, lead assessment writer for the International AS and A-Level Physics specification. He's been a physics teacher for nearly 40 years and worked with AQA for 25 years, so he's a real expert on how these exams work. He's also the chief examiner for AQA's A-Level Physics qualification in the UK. Over to you, Patrick.
Thank you very much, Alex, and hello everybody, and welcome to this webinar. I'll give you an idea of what we're going to be going through today. Unusually, this is a webinar for people who currently teach the course. The webinars I've done in the past have largely been for people coming new to the course and want to find out more about it. But today we're focusing on people that are already teach it, and we want to see what you can learn from last summer's series. Now, you'll be aware that there were 5 exams last summer. So in fact, there were 5 examiners' reports. And preparing for this webinar, I went through those reports and I looked to see what was common in terms of statements from the different lead examiners. So what we're going to be going through are things that are true basically for all 5 of the exams. Now, this thing today doesn't replace going through the reports because there's a lot of detail in them that I couldn't get through in 1 hour, and there are nuances based on different exams, the different types of exam that we do, and so it is worth reading through them in detail yourself. One of the ways of doing this is through ExamPro, and I'll talk a little bit about ExamPro later, but in ExamPro you can look at particular topics, questions and mark schemes, but importantly you can look at examiners' reports too. So an examiner's report is basically an assessment of how a particular question has performed. So what did the students do well? What did they find difficult? What can you learn from that series? And none of this is hidden. It's already published. It's on the website for you to look at. But all I've done, as I said, is try and glean those important threads that are common throughout the 5 examinations. So we will be talking about what they did well, what perhaps they could do better, and we will be talking about support. But clearly, I don't know what the constraints of your schools are. And so whilst I can talk in general terms, you'll have a better idea of the types of things that you can do with your students. But this is an opportunity for you to share in the chat. So if you have some excellent ideas, things that work for you, then please use the chat to share that so other people can do that too. So this is what you would do in a face-to-face meeting. If we were all in a room together, I would actually say, who's got some ideas? How would you approach this? Much harder, as you would appreciate, when you're doing it online, but you can use the chat to do it. So let's see what the performance was last summer. As you can see, the AS and A-level is awarded separately, and about 40% of our students last summer gained the highest grade at AS, and about 22% the A star at A-level, but slightly more if you include the A than they did at AS. And you're looking at about 20% of the candidates didn't manage to get a grade at AS, and about 10% at A-level. One of the things that is important for you to realize, these standards, these grade boundaries, are kept quite closely in line with the A-level here in the UK. As chief examiner for the UK specification, I'm responsible for the grade boundary setting every year, and I'm also obviously in this meeting determining the grade boundaries for the international papers. And the team, there's a lot of crossover between the 2 teams, and we do go for the same standard. So you want the confidence in the grading. What do we base it on? And the answer is the UK standards, and the AQA is highly respected in that regard. So a lot of things that we're going to be talking about might be to do with certain grade boundaries. For example, if you have B grade candidates that you want to get up into an A, or if you have people that might be dropping off the bottom end and you want them to be able to get the A-level tall, the sort of bottom 10%, if you like. But again, I don't know your constraints. So the things that you want to ask or maybe tell us about these are important to you, and do share them. Okay, so one of the things that we'd like to know is this your first cohort of students for A-level physics? And this is also a chance to try out the polling. So if you could please complete the poll, which should be appearing on your screens shortly, and just let us know, is this your first cohort of students for A-level physics? It should be a simple yes or no.
Thank you all for such speedy responses. I'll end the poll now. Share the results. Patrick, can you see those?
No.
Oh, you can't. Okay. So 86% of our attendees have said this is their first cohort, and 14% have said that they have taught this course before.
Okay, right. That's very interesting. Let's move on. So that gives me an idea of the sort of experience that you've had teaching the Oxford AQA. So what were the things that the students did well? And the thing to realize here, this is just a summary of the common things. There were lots of things the students did well on particular papers, but rather than focus on a particular paper, which is probably what you could do in an hour, as I said, I'm looking at threads, I'm looking at things that are common. So the first thing was the single and double step calculations. And I'll be going through an example of that. I'll show you an example of what we mean, but I think it's fairly straightforward. And generally speaking, the students are very good at calculations. The math skills are strong. They can set out their answers. We can see what they're doing. That implies that there is a weakness on the other side, which is the written answers. And clearly, if English isn't your first language, you're going to perhaps struggle anyway. But there are certain things about it that we can talk about this morning that might help them in that area later. But single and double step calculations, that's a real strength. If you give them a question that's in a familiar context, so something that they're likely to have come across either in their lives generally or in their classrooms, they tend to know what they're doing and be able to answer the questions better than the questions that are set in unusual contexts. The particular topics that seem to be a strength this summer, and again, I think this is probably common series to series, mechanics questions and kinematics, or things to do with motion, and perhaps it's the concrete nature of those topics, so you can actually see what's going on. You know, you can get a sort of grip of what the question's about because of the sort of solid nature of it. But it certainly was a strength. And then some graph work. So I have qualified that a little bit because certainly not all graph work was a strength, but taking data from a graph, so where you've got to read a point, the sort of reverse of that, taking data and plotting them as points, and then drawing lines of best fit. So these were all commented on within examiners' reports this summer. And that's essentially what I've done. I've looked at where people have said what the students were able to do. I've looked to see if that's been a common thread through the papers, and that's why they got onto this list. And then lastly there, you can see multiple choice questions. So we do get the data for how the students have performed in the first two sections of the paper and how they perform in the multiple choice questions. And generally speaking, the students perform better at multiple choice. So whereas the mean mark for the written paper might be, say, 55, 60% or something, the mean mark for the multiple choice questions might be 10% higher than that. Now, clearly in multiple choice questions, you have an answer that you know should be correct, and it gives you a way of checking your work. So if you don't get that one of the answers that are written down, you know to try again. If you've just got an open question, you can't do that. So those are the topics, and I will be going through now just some examples. So this is taken from PHO1 question 8. So this is from last summer. Question 8 was about a footballer kicking a ball And you can see it's got this parabolic path through the air and hits the top of the crossbar. So we would probably see this as a familiar context because football is so popular around the world that many countries will have their own leagues and have a national team. And so people will be able to identify with this type of question, understand what it's asking you about. So the important point being that you've got a speed, you've got an angle, so you've got a velocity really, you've got a measured distance, and then you've got the fact that it doesn't hit the ground, it hits a point higher up. Okay, and that assume that air resistance is negligible. So this means that you can just use the kinematics equations to answer the question. And we have a student's response. So one of the things you're going to see this morning is that I will be using students' answers from last summer, because when we're doing the awarding, we look at actual student papers. So I've got a lot of them that I could use when I was putting this together. And in this case, I just wanted to show you the nature of the single step and double step calculations. So the first part of it is to show that the time between the ball being kicked and reaching maximum height is about 0.94 seconds. And the student was able to do that. Notice that they wrote their answer down to 3 significant figures. That's important for the show that question. If they weren't to do that, if they just wrote 0.94, they would actually lose one of the marks. And on the right hand side, calculate the time between the ball being kicked and it hitting the crossbar. So there is 2 steps to this. They've got the first time to work out, and then they add on the essentially the time taken from the height to the crossbar, and they add that to the time taken to get to the top. So that's what makes it 2 steps. They've got to realize basically that what they've just worked out feeds into this calculation, and then they can work out a final answer. One of the things I do want to show you about this answer is the number on the answer line. It's just to be a bit careful about this, because in sort of English that would be 1.J4. And if you just saw that in isolation where 1.J4 could make sense, and then there's another point afterwards, then that's what you would read it as. But we know the answer is 1.54, and therefore we can look at that. We can look at their 5 from the previous line, and we can say, yeah, that is the way that they write their 5s. But just be wary of that with your students, because if a number is ambiguous, so it looks like it could be one number or another, the chances are the student won't get the benefit of the doubt. So try and encourage your students to write very clearly. And I understand, if perhaps they don't use the Arabic numerals on a regular basis, and therefore using them, is a bit more of a challenge, but it's encouraged. But I have to say, this answer is no worse than UK answers. They can be just as ambiguous in the way they write numbers as well. Okay, so that was one from the AS. This is a full A-level question, and this is on Planck's constant. So this may be an experiment that you've done with the students. One of the things that I would suggest is that when you go through the exam papers, you look at examples of experiments like this that can be done, and you do it with the students. With very little equipment here, you can get a value for Planck's constant just by using LEDs, voltmeter, and a variable power supply. So, and that could be a fixed power supply with a variable resistor, of course. So with very little equipment, you can actually do this experiment, and then you could use this question as an example to go through with them. But in this case, we set up the question. We'd probably see again, this might be a familiar context. It depends on the center. We say there's 6 different LEDs, and each one emits a different wavelength of light. Okay. If I just move on. And then what they've been asked to do is plot on that was figure 6 without the lines on. The values for the final data set in table 3 using an error bar for V. So all of the other ones are there. The bottom one is the final one, and they've had to make sure that that point is within half a grid square of where it should be, and then draw the 2 best fit lines that show the maximum minimum gradients. And you can see that student has done that. You can see the maximum gradient line and the minimum gradient line. In this case, they may have just drawn from the top of the first error bar to the bottom of the last, and the bottom of the first to the top of the last. And it's worked. But be careful, because it doesn't always work. You know, you could find that one of the other error bars in between those two is actually the constraining one. And it's not a good way of doing it if you just go from top to bottom like that. But it's worked in this case. There's a bit of messiness around about 1.6, 1.6 area. And that's the, that could, in certain circumstances, if it looks like they've drawn 2 lines, for example, it's got 2 gradients, then that could lose a mark. But in this case, it's been condoned. I think it's very clear graph work. So that's another example of the things that they're doing well. But the more graph work they do, then the better they're going to be at it. So, do get them to do practical work where you can plot things out. You can plot them in terms of linear graphs like this, or log graphs and log linear, things like that. More graph work, the better. Okay, so we're jumping about a bit in terms of questions. This is PHO3 question 21, where we've got an object moving in SHM, and this is a fairly typical multiple choice question. So you've got the question set up, you've got 4 options, and the way to answer it is to fill in the little lozenge ellipse shape on the right hand side. If you don't like it, cross it out and fill in one of the other ones. If you then change your mind again, perhaps you want to go back to the original answer, you cross your new answer out and draw a bigger circle around the original answer. All of that is in the paper. It tells you precisely what to do to fill this in. And it just makes life a lot easier if your students do follow that. So get them to read the rubric, go through it with them, make sure that they know what they've got to do. And one of the important things to tell them is that there is only one answer. Every time I do an exam paper, I do see people who put down more than one answer. So just filling in one lozenge is quite important. So the reason I'm sharing this particular one, I think over 80% of the students got this right. And also it discriminated really well. What that means is that those 80% were the 80% best students. So in terms of the A level, what you're looking at here is basically the E grade boundary. The students who did this well are likely to got the A level, and the ones who got it wrong didn't. It's bang on the boundary. So this is very useful. This is the sort of thing you can use with your students. You can get them obviously to answer it, but you could also get them to explain what the alternatives are. And when we write so we have to try to make sure that the other answers could be picked by people. I want to say is that even though this was answered by a lot of people, 80% correctly, it still had its role to play as far as assessing the students is concerned, because it discriminated well. So a chance for me to take a pause, and I'll just ask you, which questions do your students perform well in? Are you aware of what they do well? So there's the 3 chances, 3 choices: single and double step calculations, questions set in a familiar context, multiple choice questions. Again, if we could just do that poll, thank you.
Just a few more seconds. Okay, I will end the poll now and share the results. So 50% of you have said that single and double step calculations are the easiest for your students. 33% said question sets in a familiar context, and the remaining 17 said multiple choice.
Okay, well, thank you very much for that, because it's very helpful for us as examiners to get that type of feedback, because we want to make sure that we write exams that people feel they can have a go at. There's no point in us always setting questions in unfamiliar contexts, because whilst it might test the most able, it's not actually discriminating between anybody else. And it's also helpful to know that essentially your findings are similar to ours, that, you know, that the single and double step calculations are things that they tend to do quite well at. It's obviously in many schools, the math skills are emphasized, and so they pass that over into their physics and they can answer those questions well. Okay, thank you very much. And we'll move on. So this is your opportunity. Obviously, you've got them throughout this morning, this hour, just for you to ask any questions. Unfortunately, I can't see them, so Alex is going to have to read them out for me. But if you have a question, a burning question that I can answer, then I will do it. If for some reason I can't, then I'll make sure that I either find a person who can, or spend some more time on it so that I can answer it, and then pass it back through to Alex, who can forward it to you, I presume. But do feel free to ask questions. It's one of the reasons that I'm here. You know, you've got essentially a lead examiner in front of you that you can ask questions of, and I'll do my best to help.
Yes, please do ask Patrick any questions, and I can forward any answers that he can't give you right now. There aren't any currently, so I'm going to say let's continue, because there will be further opportunities to ask questions later on.
Yeah, okay. Thank you very much. So we've done the bit on what they've done well, and as I said, everything, it's not comprehensive because of different papers. There will have been different things, different questions that they performed well at. Do read the examiner's report, but those are common throughout the papers. So what about things that they need a bit more help with? And again, common throughout the papers, generally speaking, show that questions. Now, we saw a show that just a few minutes ago. This is where you get a value in the question, and the students have to arrive at that value. What they can't do is just write that answer down, because clearly they haven't shown anything. And so they must show some working. And I'll give you an example of that in a few minutes. Careless errors, and I think it's a major bugbear, isn't it, of all of us as teachers, where you've got somebody who's capable of doing a question, they know their physics, they can do the maths, say, or they can explain things, but then they make some careless error, and it may be due to the stress of the exam situation, it may be unfamiliarity with the context, but for whatever reason, there is an important piece of information that they miss, or there is an error that they make in their calculation or explanation that is only due to carelessness. Maybe transferring information from the page to their answer, and they get two numbers interchanged, something like that. They're very common, and they do make a difference between students' performance from one grade to another. We've already mentioned the fact that unfamiliar contexts are harder than familiar contexts, but we have to use them. One of the reasons is that teachers want to know if their students can answer questions in unfamiliar contexts. Universities do, employers do. As a physicist, it's helpful that I can answer questions if I know what the context is about. But if someone was just to ask me a question about something I'm not familiar with, the fact I can apply the physics to that is a very useful thing. Lack of detail in an answer. So this is where the answers are vague and maybe ambiguous. There is just not enough detail for the examiner to be able to tell whether they've actually hit the marking point or not. or whether they know it or not. And so, again, it comes down to practice, exam technique. I'll talk a little bit about that to give you an example. We said graph work was a strength, but practical work in general is more of a weakness, and the use of graphs rather than just the plotting of them, or maybe just getting one data point from them, that tends to be a bit weaker. So this is where you've got to work out probably an intercept or an extrapolated intercept, or maybe when you've got to do some gradient work. That's a bit weaker than the more straightforward just plotting of the points or drawing a line of best fit or getting one piece of data. And then surprisingly, I think for me a bit, I don't think I've done this many times for the UK spec. I've written the feedback for the people in the UK from their exams, and I don't think I've come across units and unit conversions as a particular issue. But for some reason, this last summer, there were several examples where people weren't able to convert from one unit to another, or they were just getting the unit wrong. So we'll have a look at a particular example. Well, we'll look at the list really of those units shortly. So these are the things that we're going to go through. There are others. If you read through the examiner's report, you'll see them for particular papers, but these are things that were common and I kept coming across when I was reading the reports. So we'll go to PHO4 this time. So as you'll see, the examples I've purposefully taken from the 5 different papers, so to show you really that it isn't just because of one paper. And here to show that question. So show that the energy equivalent of 1U is about 930 MeV, and we give them what 1U is. And the mark scheme is very clear. If we want to see the use of E equals mc squared, writing that equation down first would be a terrific first step for a good answer. Substituting the m 1.661 times 10 to the minus 27, substituting in 3 times 10 to the 8 with a square around it. That'd be a good next step. And then we're looking for a particular answer. And we're looking to get 934 to at least 3 SF. And that is important because there is a unit, a U value on the data booklet. And you'll see in a minute the people who used that and so basically didn't answer the question didn't get the mark. But here is the mark scheme. It's a fairly typical mark scheme for us in that each marking point has a tick associated with it, and there's 2 clear marks. And here's 3 answers. Now, we haven't got time for me to ask you what marks you would give them when we've about halfway through now. So I'll just go through it myself. So the first answer is on the left-hand side, the top 2 lines on the left-hand side. Remember what we're looking for. We're looking for E equals mc squared for the first mark. There's no evidence of E equals mc squared there. I think this answer is basically fiddled because 931.5, that also isn't the answer we're looking for. We're looking for 934, remember. Here, what they've done is taken the one in the data booklet, realized in order to get to that answer, you've got to multiply by 5.61 times 10 to the 29 without any reasoning, and then write that down as the answer. You won't be surprised that that gets 0 marks. Now, to the right of that, you've got your E equals mc squared written down. As I said, that's a really good start. And whilst that on its own wouldn't get the mark, then the substitution of the next part of the answer does. So 1.661 times 10 to the minus 27 times 3.0 times 10 to the 8 squared. That's precisely what I said a few seconds ago. That would get the second mark. Yeah, sorry, the first mark. So E equals mc squared, they've used it. What have they done then? Well, again, they've realized that there is a value for the answer, 931.5, and they fiddled it. So they've taken their value in joules, multiplied it by the thing that would give them that answer, and written that answer down. So that gets the first mark, but not the second. So let's have a look at the bottom. Equals MC squared, good start, good substitution. But they've gone straight into converting that into EV. Well, that's fine. I can see what they've done. They've divided it by a charge on the electron. They get the 934.3 that we're looking for, times 10 to the 6 EV, and then they've replaced the 10 to the 6 by the mega, and there's their show that answer. So that bottom is a perfect answer. That's both marks. So you can see, knowing about this sort of thing, now this is something you can warn your students about, that when they've got to show that value, even if it's trying to show them something that's on the data booklet, don't just fiddle that answer and work backwards, because it could be, for some reason, that it's a different answer when they actually work it out. So in a sense, the honest answer here is the bottom one, and it gets both marks. Lots of things about show that's that students fall down on. One is not setting out that answer, so you can't actually see what they're doing. The first answer doesn't start with an equation. It'd be quite difficult to, in some circumstances, to give that the mark, because you want to see they know what principle they're using. And also this idea that if you have a value in the question, you give it to one more significant figure when you write the answer down. So if we're asked them to show it's about 934 MeV, then you go to one more sig fig, 934.3 in your answer. And that just shows us as examiners that they've actually worked it out. If you just say which equals 934, they maybe just didn't bother putting the numbers in the calculator, didn't work it out or anything. So it's very helpful, and in fact it's essential that they give it to that next significant figure. Let's move on. So PHO5 now, and PHO5 is a difficult paper. As you know, PHO5 doesn't have any objective test questions, and we know that they're the things that the students, multiple choice questions, they're the things the students tend to be quite good at. The contexts tend to be quite difficult, because those contexts have to be set so that you can ask different parts of the specification about them. So you need a context that you can ask mechanics questions and electricity questions about, say, and maybe thermal questions. So you can see that PHO5 is a difficult paper, and the main thing I can suggest to improve the students' work on that is practice. There's quite a lot of PHO5 papers now in the on the website, in the bank, if you like. Get your students to do them. Get the students to do those questions with the mark schemes, so they can see the sort of things that people are looking for, with the examiner's report, so you can see the common errors that people make and the things that they did well. But as you're leading up to this exam, practice, practice, practice. The more questions they can do and get feedback on, the better. So anyway, this is a question which sets up a situation with some water coming out of a sprinkler, and we've got another show that the speed of the water as it emerges from a jet is 8 meters per second. And you can see that you've got 3 steps, essentially. You've got the calculation of either the volume or the mass flow rate, the area, or deals with 24 jets. Either of those would get a mark, and then you've got the final answer. On the right hand side, you've got the sort of thing that you might see. So we're looking for 1680 divided by 3600, and we're looking for 2.44 times 10 to the minus 6, or a division by 24. It just helps the examiner and you as a teacher, when you see it on a mark scheme, to see what we're looking for. So immediately I can see a 1680 divided by 3600 on the second line. So I'll be mindful of giving the first mark. And then I can see a divide by 24 at the bottom. So that's the second mark. I think the second mark is also given for the other part, just above that. But they're not getting the same answer as the third mark, and we are looking for that particular answer. 7.96 was it? Well, they're getting 8.025. Why? Well, I think it's on the second line that they've done a rounding error. They say it's approximately 0.47. And so that meant that their final answer is rounded wrongly, as it were. 8.025 is not correct if you round to 0.47 on the second line. So this is another point I'd make with your students. Do not round early. And it isn't only true for show that questions, but don't round early, because if you do, you could be penalized for it in the later part of the question. Here, the number of significant figures is important, and therefore you shouldn't round early. You shouldn't use 0.47. You should keep it, well, 7/15 if you like, or whatever that is in your calculator to however many significant figures your calculator works to. So that only gets the 2 marks, even though they knew precisely what they were doing. It was an error, really, in the understanding of expectation that's cost them a mark.
Just while you pause briefly there, Patrick, I have a question from one of our attendees. So considering with regards to the significant figures, so how many significant figures would the examiners expect from the student's response? I'm assuming that would be what would be stated in the question.
Now, if it's a question that says, give your answer to a correct number of significant figures, then they've got to use the least significance of the data that they've got. So in this case, that would be 2SF, because 8.0 meters per second is only 2SF. But it would say, you know, give me the correct number of significant figures. If it doesn't say that, for normal, if you like, questions, we accept anything from 2 upwards. So more than 2 sig fig up to 9, whatever your calculator does, not penalized. There are a couple of exceptions. One is show that. So show that, we always look for one more sig fig than the show that value. So 8.0 should be 8, 7.96. In fact, that wasn't data, was it, the 8.0? But the other one is where it's an integer. So if it's the order of a diffraction grating, which is a whole number, then that should have a 1 sig fig answer. So it would be 1, 2, 3, 4, whatever. Now, all these rules are essentially set out within the examiner's reports when people come across it. But that's the general idea on significant figures. I hope that was helpful. If that wasn't clear, then I can send you an email with it written down if you want to ask it again, or listen to it again when you get a chance. Okay, moving on. So this is another PHO5 question. Look at the amount that the student has to read. There's just a battery with a bit of circuitry underneath. And what they're asked to do is complete that very simple thing to show how it's connected to the thermistor to the battery. So there is a thermistor in another part of the diagram, include the additional components. Now that's the command sentence. The important information's before that. He connects the thermistor to the battery using a potential divider, and that allows him to adjust V. Now it's carelessness if you don't read that. You don't take that into account, because there's no where you can do it, get the mark, unless you use a potential divider. So let's have a look at a student answer. Now, they've taken the point that you need an ammeter and voltmeter. That was there, so that's okay. But there's no way of varying the voltage here. There's no potential divider unless they think the potential is divided between the ammeter and the thermistor. This is not an answer to the question. Now, they clearly know things, don't they? They know a voltmeter goes in parallel and an ammeter in series. They know how to connect the circuit up. So why is it that they've missed out the important part of the answer, which was the potential divider? So one of the things I want to point out about this answer is that this student was on the grade A boundary. So I chose this from a paper that was just 1 mark below the boundary when we set the boundary. And this answer cost them the grade A, if you like, but there being other answers in the paper too that did it. But you could say that this carelessness cost them that grade. So do highlight the importance of reading the question and answering the question to the students. And whilst that might sound a bit glib, of course you read it and answer it. This student hasn't, and this isn't a very able student. This is a grade A student, but they've missed out on the grade A because of that. So do avoid carelessness. Do read the answer very carefully. It's always pleasing when I'm marking papers, when I see keywords underlined. So the student's actually gone through it and thought, potential divider, must underline that because that's important. So going back to PHO3. So this is a question about the capacitor. So again, probably it would be familiar. And this isn't the first part of the question. So the questions led up to this point. So we've had four different question parts before now, where they've done calculations. Essentially, I think they've just worked out the capacitance as they went through it. Resistor, time equals 2 naught, capacitor is uncharged. And then it has to sketch the magnitude of the current, because the direction will be opposite, as the capacitor charges. So essentially, the circuit's the same, except it's charging. What does the graph look like? And very helpfully, we've given them a dashed line that showed them the previous graph. In other words, what the discharging circuit was. And whilst we say it was helpful, it was also allowing us to check the detail in their answer. Because the answer is, as you know, the line follows the dashed line. It should be exactly the same. So we'll have a little look at what the mark scheme says. So there's 2 marking points. There's a line with decreasing negative gradient. So as it was, that dashed line has got a line with decreasing negative gradient, and it follows that dashed or dotted line on the graph. Now, the other thing is MP2 is contingent and MP1, and that's obvious really, because you couldn't have MP2 if you didn't have a line that was decreasing negative gradient. And then it says, do not condone a line that ends abruptly at the time axis. Now, I would go through mark scheme like this with the students to help them. And that do not condone is quite an important thing. We use the word condone to say, basically, we know this isn't a good thing to do, but if you do it, you'll still get the mark. And obviously, do not condone is the opposite. So we don't condone somebody who does this. We don't give the mark to somebody who does this. If we'd have said do not allow a line that does that, that would mean they'd get no marks for this question if their line ends abruptly. In other words, they didn't go all the way to the end of the dashed line. And in MP2, do not condone a line that is consistently above or consistently below the dashed line. So we're allowed some variation because it's difficult to follow that dashed line exactly. Anyway, I'll show you an example of an answer. So we have a chance for another poll before I go any further. There is 2 marks available here. So is this going to be worth 1 mark, or do you think it's going to be worth 2 marks, or in fact, do you think this is worth 0 marks? So if we could have that poll.
So this poll has not been set on the options. However, if you'd like to drop your answers in the chat, I can read them out.
Oh, that's good. Oh, I'm sorry about that. Right. Oh, I was looking forward to this one as well, because it's always nice as an examiner to see how other people mark things. I'll give you a minute then, and then Alex will tell me if you've had a go.
One respondent said 1. The attendee who says that they can't see the poll, there is no poll running live. Please put your answer into the chat.
Yeah, sorry about that.
Someone said 2. In the interest of time, I think another attendee also said 2. I think in the interest of time, we carry on, please, Patrick.
That's okay. Yeah, I understand. Some people don't like to commit themselves, and as well, and want a bit more time to think about their answer. So that's all commendable too. So this would have got 1 mark. It's certainly got a negative gradient, and that decreases. So it's getting the first mark, and everybody agreed that gave a mark. But it didn't get the second, and it does leave the dashed line behind for some reason. And I think the reason is they want it to be 0 after 10 seconds. So they've done that mistake. It's sort of reaching the naught line. In the 10 seconds, it wouldn't have done. And so whilst this is somebody who has partial knowledge, if you like, of what's going on, at least they know it follows the same shape, they've for some reason thought it's got to be fully discharged in that length of time. And there's no reason for that. So in fact, this would have got the first and not the second mark. But you can see how that would discriminate, because somebody who did realize that it wouldn't get down to 0 would have got both marks. And so they are your more able physicists getting both marks. This is a very easy question to mark in that sense, because we've given the answer on the paper for them to look at. But I would get your students to do what I've just done with you. I'd get them to mark it, or get your students to do it and then pass them around the classroom and do it anonymously, if you like, share them out, get them to mark each other's, and maybe give some feedback as to what they could do to correct it if they'd got it wrong. That is all, important learning experience for your students. It's certainly something that I've done quite a bit in the past. If we move on, these are examples of question context. So I did say that question context is an important thing here. So I went through the 5 papers from last summer, and I wrote down what I saw as the context from electron-positron pair production in PHO1 all the way through to uranium ores and natural fission in PHO5. Look at that. If you did the whole 5 suite last summer, you were asked questions on such a huge range of topics. How can you be prepared for that? If I move on, these are the ones that are engraved, I'd say, are likely to be less familiar. It depends on how you teach or what you teach them. But you can see the substantial number of unfamiliar contexts, particularly in PHO1 for some reason, but also in PHO5. I've sort of contradicted myself there, thinking football was no longer familiar, but we don't know for a lot of them. But certainly garden sprinklers, it's not really a familiar context, is it? Natural fission, unless they've read about it. That's the sort of thing that we'd expect the students to be able to answer if they're very able. Space station question, an orbit and space station, interrupted pendulum. These things you have to get your students prepared for. So I'm not sure if this is a poll as well, but we are running about a time. So we've got about 10 minutes left.
This is a poll. I can see if I can reshare it. There we go.
So just some ideas in that poll. I can't even remember what the options are now. Lest I do, your own ideas, past paper questions, textbooks, or internet resources, or other. And maybe you do more than one of these things.
Thank you for your participation. I'll end the poll and share the results. So 50% of our attendees have said that they prepare students from unfamiliar contexts with past paper questions, and the other 50% said textbooks or internet resources.
Okay. Yeah, and that's fine. And I just reiterate, the more past papers you do, the better. But clearly, if a student's got a particular interest, it's quite helpful to be able to use that with them if they need to learn about a topic. If you can say, well, what do you know? Have you come across anything, and ask questions to do with that? That's helpful, and then use that with the rest of the class because it's going to be unfamiliar with them. There are lots of things you can do, but you have to keep, I would suggest, plugging away at this fact that they're going to come across situations that you haven't thought about before. And whilst you can't prepare people for that explicitly, you can't say, right, you're going to get a question on this that you haven't come across before because you won't know. You can get them used to have the flexibility of approach. That means the important thing is the physics. Look at the situation, look at what you're being asked. The situation really is just a hook that the question's hanging from. Once you've got some idea of that, it's most important that you know what the physics is that you're applying. Apply that physics, and the chances are you're going to get the right answer. But yeah, practice, I guess. So just an example of a question which has a context. Our school, I've always taught in schools that had one of these. Maybe you haven't thought about how it's designed, but look how much the students has got to read the diagram, the detail on the diagram. If they're not familiar with this, do they know how to approach a question like this? Underlining key piece of information, making sure that they've just got that idea of what the physics behind this is about. You can see pluses. You're likely to be thinking in terms of charges, aren't you? Anyway, but it's a VHO5 question, so we could be asking about the motor as well. We could be asking about moments on the motor and torques. This is an example of a question from last summer as well that you can you see an interrupted pendulum. That's maybe a context they haven't come across before. The idea here is that they didn't give sufficient detail. If I just flip back one, the question is, how do you know there's no energy transferred from the system? And the point being that maximum value for Y is the same. A lot of people said it's because the amplitude was the same, but the thing is, Y, if you look at the graph, wasn't the amplitude when you look at the situation. So this is a question answer that nearly gets there. The amplitude is constant. That's wrong. Means that there is a constant total. That's true. K and P throughout the oscillation, which means no energy is being transferred outside the system. What they needed to say really was the maximum height it reaches is the same. That's the value of Y. And at that point, it's got no KE. It's all PE. And therefore, the total energy is the same. It doesn't lose any energy. Okay. The amplitude is constant again. There's a constant total energy. So this is the same answer, but there's the mark scheme. When Y is a maximum, all the energy is potential, and that Y is a constant. Okay, get your students to write down the detail they need. And a practical question, did they get this right? The important thing here, the situation's probably one they should be familiar with, but if you're asked to measure a distance and you've got multiple points to measure it, then don't just choose a distance between two single points. Go across the whole width of the diagram and divide by the number that you've got. Otherwise, you won't get a precise answer. So that sort of important practical skill the students need to have. And then plotting a graph, if you can see it, the bottom scale isn't linear. It goes 5, 5.5, 5.75, 6. That's a non-linear scale. It's a careless thing to do. But the more graphs that you plot where the data is a mixture of numbers that aren't on the scale, if you like, then the less chance they have of getting that wrong. But that's just carelessness, poor graphing skills. Just getting the scale wrong. It was very common on that paper. Other things they get wrong: not using a large triangle, trouble sketching sine curves, so get them to practice sine curves because it's quite common, and determining an area under a curve, adding squares, different shapes. All of that is in the examiner's report, but these are common graph errors. So where I said they were good at graphs, this is the sort of graph work they're poor at. Units and unit conversions, this is the last thing to share with you. What they're getting wrong: powers of 10 and subscripts. I don't think that should say subscripts, but I think what that means is actually the thing before the unit. I think subscripts is the wrong word there. So things like nano and pico and stuff. MEV to joules, degree C to Kelvin. These things the students were getting wrong. Kilograms, degrees K and little k. So using a little k for kilogram and a capital K without the degree sign for Kelvin. That was a common mistake. And then if you've got joules per kilogram per Kelvin, don't write it like it's written there, but use the kg minus 1, K minus 1 method. But it's important to emphasize units. Perhaps they're forgotten sometimes. So do make sure that you go through units with your students. And then use the formula, which wasn't on the list, but surprisingly, people getting the wrong formula for areas and volumes, this volume of a sphere, the surface area of a sphere, getting confused between them. And if a question is asking you about an area and they give you the diameter, people use that for the radius. That was fairly common. Careless mistakes again. The equations for areas and volumes they need to know, they're on the data sheet, so they should be able to just find them and use them. Common errors. Okay,